Today we're going to be focusing on section 2.6, which is on that of rational functions. And rational functions is really just looking at a ratio of two separate polynomials. So at the top of your page you have a little definition of it where it's n of x, numerator in terms of x, over d of x, denominator in terms of x. And the key piece about rational functions is that where the numerator function can be constant, like the number 3 or 1, the denominator has to always have at least one x term in there for it to be a rational function. Now, the big thing we're going to be focusing on today in terms of this form, this little extended form we have, are our leading coefficients, the a sub n for numerator, b sub m for the denominator, and then these kind of leading degrees as well. So x to the n, our degree up top, and m, degree down below. But first, a little reminder about some stuff about rational functions before we dive into some new stuff in graphing. And like normal, we always come back to dealing with domain right off the bat. So if you remember, domain is where our inputs are allowed to exist, where that graph's allowed to exist. And for us, for rational function, that's any and everywhere except for where the denominator is going to be equal to 0. Can't divide by 0, we get undefined. So what we want to do is we want to find out where that's going to be 0 so that we can exclude that from our set. So for our first one, x minus 2 is 0. We get x is equal to 2. Now again, this isn't part of our domain. This is actually everywhere the domain doesn't exist. So if I were to be writing out my domain, we have our interval notation, negative infinity up to 2. Don't get to include it. But everything from 2 up to infinity is good to go. Oops, not 8. To infinity. Very similar with number 2. For number 2, although this has maybe a little more going with the numerator, it's still only dependent on the denominator. So we set it equal to 0. Now this is really nice, right? It's a linear term, so we just get x is negative 1. And that's where we have an issue. However, in more complicated cases, we might see that this is quadratic down below, or even something more, where it's really going to test your ability to kind of find the zeros of that function. But if it's something linear, really nice for it. So a little reminder, domain is where we have zeros in the denominator. Now to something that we haven't kind of seen for a while, which is dealing with asymptotes. Those were those lines, sometimes called fences, and those graphs that we can't cross over, either vertical or horizontal. And there's a bunch of different ways to find these. So first off, we're going with vertical. And vertical asymptotes come from the denominator. So our vertical asymptotes are, well, really similar to this. It's where the denominator can't exist. It's where we have these gaps of definition. So for vertical asymptotes, this is where our d of x is equal to 0. That's where our denominator is equal to 0. Now, one little key piece is not like terms, I'll say shared terms. We need to make sure we don't just look at the denominator for vertical. So that is the starting point, don't get me wrong, but all of our vertical asymptotes are going to be kind of the factors of the zeros of the denominator that are not also shared with the numerator. And we'll kind of see an example of that as our first one. So when we're looking for asymptotes in general, for vertical, we want to factor the top and the bottom, cancel out any of those shared terms, and then after that, what's left over in the denominator, those are going to be our vertical asymptotes. And we'll see an example of what we mean by these shared terms with number 3. Now for number 4, or not number 4, when it comes to horizontal asymptotes, jumping the gun, we have 3 different cases. And this is all dealing with degrees. So instead of having to factor for the horizontal, we're actually just comparing the numerator and denominator. So n, again, is our degree of the numerator, m, degree of the denominator. So if we have the top degree is less than the the bottom degree at all, then we get the really easy case of y equals 0. Y equals 0, right on that x-axis, an asymptote where you can't cross it. So for example, if we look at number 1, doesn't quite fit that, right? Because they have the same degree. Number 2, they have the same degree. And in fact, all the examples on this first page have the same degree, so actually none of them would have this real basic given horizontal asymptote. But they do have this next case. If the degrees of the top and bottom are equal, then we're going to be looking at a ratio of the leading coefficients. So again, if we have our degrees out front, everything in standard form, the leading coefficients are those on those leading terms. Now, let's kind of relate this to the few examples on this page. For number 1, they have the same degree, top and bottom. That fits this. So you look at the ratio of the top leading coefficient over the bottom, which is 4 over 1, or 4. So y equals 4, so up 4 from x-axis, we would have a horizontal for this one. For example, number 2 would be 2 over 1, because they're the same degree. So y equals 2 horizontal. That extends also onto things like number 3 and 4, but we'll work those out in a second. Lastly, we have the case where the numerator degree is larger, and when that happens, we have no horizontal asymptotes. No horizontal asymptotes are going to exist if the top degree is larger by 1, 2, 3, 4, anything. As long as the top is larger by at least 1, we have no asymptotes. Now, let's do a little bit of practice of finding these asymptotes specifically so we can kind of flesh out this idea for that vertical. So looking at number 3, we have two quadratic up top, quadratic down below, and we want to find out where we have the zeros down below. So we'll start with that. So let's start with factoring the denominator. So x plus 3 plus 1 down below. And although I just want to jump to it right away and say, oh, x minus 3 and x minus 1 are vertical, we want to make sure we look at this right here. We want to look at the top as well, just to make sure there's nothing to cancel out. So we want to factor the top. So 3x squared, so 3x and x. Negative 6, we'll do minus 2 and plus 3. So we get the 9x and the negative 2x. Now, although we're not going to pull information from the top, we do have these shared expressions, right? The x plus 3 up top and down below. Now, when we cancel those out, we'll make note, we're going to see it down the row that this is going to be called a hole in our graph, and we'll get to examples of that for now. But when we find those repeats from top and bottom, we remove it from the vertical asymptotes, which only leaves this x plus 1, or vertical asymptote at x equals negative 1 for the vertical. So again, vertical, kind of want to factor both. Cancel out any repeats, any shared expressions, and then whatever's left over in the denominator will be your vertical. Now for horizontal, just like our other two cases we already talked about, the degree is not smaller up top. In fact, they are equal. So we have y equals the top leading coefficient of 3 over the bottom, which is 1. So y equals 3 over 1. Or we can simplify that. Just y equals 3. Now, a thing to note here is we have exclusively 3 cases for the horizontal. It's either y equals 0, y equals some constant, or not existing at all. For vertical, imagine they didn't share this top term. You could have 2 asymptotes, technically 3 or 4 or 5. So there's no limit on the number of vertical asymptotes, but there are in horizontal. You can only have 1. That brings us to number 4. Like normal, give it a pause. Do what you can, fully factor top and bottom. Repeat. Any repeats cancel out to get your vertical. And then apply one of these 3 cases to get your horizontal. We'll work it out in just a second. All right, hopefully you give it a shot. So for number 4, gotta do factoring. We can do both at the same time, but at the top there's nothing to factor, just that 5x squared. And at the bottom we have those differences squared. We get x plus 1 and x minus 1. Now, for this case, unlike number 3, there's nothing to cancel up top or bottom, right? Which means we have 2 vertical asymptotes. One at x equals 1 and one at x equals negative 1, which is fair, right? We have a bunch of verticals. And then lastly, you're looking at, for horizontal, what are our 2 degrees? Oh, degree of top is squared, down below is squared. Same degrees means we look at the ratio of those leading coefficients, which for us is 5 over 1. Y equals 5 over 1, or we could simplify that to 5. Which means up at 5, we would have a horizontal asymptote, and at x equals 1 and negative 1, we would have vertical. So now we know how to find these things. Let's look at some basic graphs and some special cases. As we hit that bottom of the first page, we're going to be looking at our first base case of graph and rational function. And with each of these, we don't just want to graph it, we also want to state the domain. So just like we did right up above, to graph it, we want to find our asymptotes first. We'll find both of them. From there, we're going to test a couple points to the left and the right of each of our vertical asymptotes, and that'll help us kind of get that general shape, which will then pull the domain from there. So for starters, for number 5, we want to find our vertical asymptotes. Again, that's where the denominator is equal to 0. For here, it's just x plus 3, right? So set that equal to 0. We subtract the 3, we get x is negative 3. So at negative 1, 2, 3, we have a vertical asymptote. Now, equally, we have our horizontal asymptote. We're comparing the degrees at the top and bottom. We see the degree down below is 1, and the degree up top is technically 0 because there's no x's. That's the case where the top degree is smaller, which by default throws y equals 0, so that x axis as our horizontal asymptote. Now, very helpful to do the next pieces. Well, if we remember that general shape, the rational kind of had 2 pieces, looked a little bit like diagonal parabolas, a touch. But we got 4 different quadrants we just created, right? So we want to know where it's going to be. So it's best to kind of test a few points. We've got negative 1 here, negative 2, we've got negative 4, negative 5, because right at negative 3 we have that asymptote. So we should test a little on the right, a little on the left. So let's start with f of negative 1. Plug in negative 1, you get 1/2. Oops, we'll do f of negative 2. Plug in negative 2, you get 1 over 1, or 1. So we know to the right of this vertical asymptote, at negative 2, we go up 1. And at negative 1, we go up 1/2. So we're going to have it curving like that. I'll kind of kill off these numbers just to kind of clean it up a bit for us. Now, when it comes to our other side, we had negative 4 and negative 5, so we have f of negative 4. Plug in negative 4, you get negative 1. And f of negative 5, you get negative 1/2. So we get negative 1, and then negative 1/2. So now with a couple points in those quadrants, we can kind of finish it off. And we can not only connect the dots, but we know we're never actually going to cross over those asymptotes. We're just going to keep getting closer and closer and closer and closer and closer as we kind of go out to infinity. And then we got something similar happening down over here. Again, at no point are we crossing those asymptotes in this case. Now, lastly, we need to find our domain. Well, the only x value we see here that's being excluded is that of negative 3. So everything but negative 3 will be included in our domain. So again, find our 2 asymptotes. We're testing a few points on either side of our vertical asymptote, give it that sketch, and then we get domain from there. So I'm going to have you guys try number 6 on your own. We're going to come back to it kind of worked out, and we'll kind of talk over it, and then we'll work out number 7 together. Hopefully you gave number 6 that solid try. Run through real fast. Vertical asymptote from our denominator. X is -1. Vertical asymptote, can't cross it. Horizontal asymptote of y equals 2. We have our degrees that are the same top and bottom, right? So we gotta look at the leading coefficients of the top over the bottom. That's the 2 over 1 or 2. So if we go up 2, all of that. Horizontal asymptote. Tested 2 points to the right, f of 0, f of 1. 2 points to the left. We got f of -2, which gave us a -1. Write those in, and then at -3 we got, sorry, not negative, +1, and then a positive 1.5 for f of -3. Now we know which of those quadrants those curves are going to be lying in. We can kind of finish sketching them off. Again, they're never crossing the asymptote, just getting really close. And then our domain, which is connected right with our vertical asymptote, we see that it is excluding the point or that whole section of x equals -1. Now, that's 2 examples of some basic cases. Here for number 7, we're going to have something a little bit different. So right off the bat, let's go ahead and work out for our vertical asymptotes. So again, for vertical asymptotes, we like to factor everything, make sure you have no repeated roots, repeated factors. So we got 3x up top. We have x, right? X, and it's going to be -2, so +2 and -1. Now, nothing cancels, right? So that's telling us now this is a case where we have 2 vertical asymptotes. One at x equals 1, and the other at x equals -2. So x equals 1, and then at x equals -2. Which already is looking a little weird, right? Because we know the general shape of the rational, but now we got this weird middle section and what's going to happen there, so we're going to have to play around with that in a second. Next on our list, horizontal asymptote. This one's nice and easy. Degree up top is 1, degree down below is 2, degree up top is larger. By default, that's y equals 0, or just our x-axis. Now, like normal, we want to test some points, but it's kind of funky, right? We have quite a few points to test. So I'm going to test a few things to the left of this first asymptote. So we'll look at f of, that's -1, 2. Let's look at f of -3 and -4. We'll get an idea kind of is it working on the top or the bottom. For this middle piece, let's look at f of -1 and f of 0. Hopefully that'll give us enough information. And then lastly, we'll look at f of 2, and we'll look at f of 3. So f of 2. Now, with some of these rationals, like our first 2, it's not so bad to plug values in and be able to just test them out by hand. But if you start to get stuff that's going to be squared or cubed, etc., feel free to grab a graph from calc, go to your y equals, type in your function, hit second graph to get to our table, then we can quickly kind of pull these points from it. So let's do -4, we get -1.2, -2.25. So if we go to -3, -4, -4 is at 1.2. Then -3 was at -2.25, so a little past that. So about here. Now we got our 2 in the middle. We got f of -1, that's 1.5. F of 0 is 0. So f of -1 is 1.5. F of 0 actually doesn't give us an error. It actually lands right on the origin. But that's also hitting our horizontal asymptote. We'll come back to that one. Let's look at that far end of the f of 2 and f of 3. we get 1.5 and 0.9. So f of 2 is 1.5, f of 3 is 0.9. So here's the deal when we end up having multiple vertical asymptotes. On our extremes, the ones that are kind of opened into infinity, they're always going to kind of hold that same shape as our traditional rational. So our all the way to the left piece is going to look roughly like this. And the piece all the way to the right is going to mirror what we know as a rational function. Now again, these could be flipped, but as we see, they're all positive, so that's just a reflection. But anytime we have the middle slice, so 2 or more vertical asymptotes, for every middle slice that's kind of enclosed on both sides by an asymptote, we need to test a few more points. So here I'm going to test 0.5. Here a little closer. So if I also include f of 0.5, I'm going to end up with negative 1.2. So 0.5, negative 1.2. Now for myself personally, I already know now I have enough information, but here's the deal every time we have 2 or more vertical asymptotes. All of those middle slices, so midsections, they're going to take shape of 1 or 2 things. They're either going to be roughly a parabola, or they're going to look more like our cubic function. So in order to know which it's going to be, like we just saw, those 2 points weren't enough. However, if we see now with that third, it crosses through the origin and continues down towards negative infinity, we have enough information to know that that middle section is going to look roughly like a downward facing cubic. So big thing to pay attention to. Anytime we have more than one vertical asymptote, again, the edges, the extremes that go off into negative and positive infinity, those are going to be fine. 2, 3 points, plenty for us. But any of those middle sections, we want to make sure we're testing as many points as we feel we need, I would say 3 or more, to know that general shape. Is it going to be a parabola somewhere in that middle section, or something more cubic? Now we got one last piece for this number 7, and that's our domain. For domain, everything from negative infinity, we're good, up until first vertical asymptote at negative 2. Then we got a union. I'm going to kind of write this down because I'm running out of room. Union from negative 2 to our next vertical of 1. And that's union one more time from x equals 1 to positive infinity. So here's kind of one of our special cases. We have 2 or more vertical asymptotes. We really got to be paying attention to those middle sections. That's where it's going to get us. But now we got one more type of special case, and that's looking at when we have some holes in our graph. As we mentioned on the beginning of that first page, there is going to be a special case when we come to finding vertical asymptotes. Well, one we just saw, we had more than one. Another is when we have those shared factors in the numerator and denominator, and those terms we cancel out become holes in our graph that we don't get to include. So here we're going to see some examples of that. So first off, we want to find our vertical asymptotes. And for vertical asymptotes, it's really helpful to get a factoring of your rational, top and bottom, just to make sure you have nothing that's being repeated. So up top we have x plus 1 times x plus 1. Oops. And down below we have that difference of squares. So what this tells me is, well, normally I would say x equals 1, x equals negative 1, we have vertical asymptotes. However, we do have this repeat of the x plus 1 term. So I'm going to make a note. We have a hole at x equals, sorry, not 1, at x equals negative 1. So where we'd solve for that. Which leaves us only with x equals 1, solve for this equal to 0, for our vertical asymptote. Now when it comes to the horizontal, Horizontal, this one's, again, kind of nice and handed to us. Degrees are same. We pull from both leading coefficients. So it's y equals, well, 1x squared and a 1x squared, so 1 over 1, or just y equals 1. There's our horizontal. Now, I don't know where yet to put this hole, because I don't know where that graph's going to end up. So before I even apply this, what do we want to do? We want to test some points to the left and to the right. So I'm going to test f of 0. I'm not going to test f of negative 1. Well, why? Because I already know there's going to be an issue there. So I want to go one more over, not at negative 1, but at f of negative 2. Then on the right-hand side, f of 2 and f of 3. One more time, if you got a graphing calculator, speeds up this problem of testing points real quick for us. You can plug them in by hand, but you might as well save yourself some time. We get f of 0 is negative 1, so it's 0, we go down to negative 1. F of negative 2 is, we get 1/3, or 0.3 repeating. So at negative 2, we're up at 1/3, which means at f of negative 1, where I cross through that point, I'm going to be having not a closed circle, but an open circle, right? Because that is this point we can't include. So again, when we have those shared factors, top and bottom, it doesn't produce an asymptote right there, but it does produce a hole that we don't get to include. So I'm going to make note of that with that open circle. Now f of 2, I get 3, so at 2 I go up 1, 2, 3. And f of 3, I end up with f of 3, I get 2, 3. So now when it comes to graphing it, that right-hand side, pretty straightforward, right? We know it's going to be going along the asymptotes, hit those 2 points, continue out. But on the left-hand side, we don't want to just quickly race through and sketch that, because we want to exclude where we have this hole at negative 1. So it'll be that same general shape, but we're going to be ignoring that point. Now, if we need to also include domain, or on our last example, we had that whole asymptote, so we knew to not include it. Little detail here is we need to not include this as well, right? We don't get to include those open circles. So when I'm looking at domain, I want to go from negative infinity up to negative 1. And I want to go from negative 1 to positive 1. And then running out of room right there. But then lastly from 1 out to infinity. So whether it's an asymptote or multiple of them from having a bunch of different terms in the denominator, or if we have that shared factor canceling happening instead, and it's a hole at that point, either way we'll exclude those points from our domain. So now I'm going to have you guys pause and give the same thing a shot to number 9. I'm letting you know there's going to be a hole at least one spot. We can't have multiple holes, right? If a bunch of factors are shared, we just have multiple points we don't include. So I'll have you guys give number 9 a shot, and we'll come back and work it out together. Coming back together on to number 9. Already got it worked out. So for number 9, we factor the top and bottom. The top we get x plus 2 times x minus 2. Denominator x minus 3x plus 2. Those shared x plus 2 terms we cancel out, telling us there's going to be a hole at x equals negative 2. Now without testing the points, we don't know where that hole is going to be yet, so we leave it to the side until we've tested points down the road. So first things first, every time we get our vertical asymptote, it is whatever is left over of our denominator. So that x minus 3 term tells us at x equals 3, we get that vertical asymptote. Horizontal asymptote, that's looking at degrees of top and bottom. Again, shared degrees, they're the exact same. So we look at the factor of the top coefficient, leading coefficient, over the bottom. Well, 1 over 1 is y equals 1. Horizontal at y equals 1. Then we test a couple points left and right. I tested f of 1 and f of 2. I got 1/2 and 0, so it's kind of on that lower side of it. And I tested 4 and 5. That's something on the upper side of the horizontal. Now, knowing this right here, that f of 1 and f of 2 knowing I'm going to have that rational piece down in this quadrant I made, tells me roughly where that hole should be, which is along that asymptote as I get closer and closer to it. Now, lastly is to state the domain. So as we go to this one, domain is negative infinity until that hole at -2. Then we're good to go from -2 all the way to our vertical asymptote at 3. Then from 3 out to infinity, we're able to continue with that rational function. So reminder, anytime we're doing rational graphing, first thing I'd really do always is just factor everything as much as you can into linear terms. That way you can see any canceling or find your asymptotes really fast, rather than kind of having to go back and double check. And what we've seen so far is when we have degrees that are equal, or the top degree that's smaller, but now we're going to see what happens when we have the degree up top larger than that down below. When we went over the horizontal asymptotes on the first page, we had 3 different cases on there, but one of us kind of told us nothing, right? We had the first, that's when the numerator had a larger degree than the denominator. We had this, and then that just gave us y equals 0. The second, where the degrees had to match top and bottom, and then we looked at the leading coefficients and a ratio of them, y equals equal to that. And the third was when our n, so the degree of the numerator, was greater than our m, degree of the denominator. And what we got was there doesn't exist a horizontal asymptote there, which is true. Now, in a very special case, when the degree of these two, so the degree up top, is larger by exactly 1 than the degree down below, and here's what I mean by that. It'd be, say, x squared over x. That could be an x cubed term over an x squared term, x to the 4th over x to the 5th over, say, x to the 4th. Anything where the degree up top is larger by exactly 1 than the degree down below, we can do what's called finding slant asymptotes through long division. Now let's talk about that for just 1 second. If it is off by exactly 1 degree, well, we know that quotient has to give us only a linear term out of it, right? Because ultimately we'll do long division. How many times does x go into x squared? Just x times. X times what is x to the 5th? 1 more x. So it's always going to give us some line, something linear, as our quotient if the degrees are off by exactly 1. Now, for the 2 cases we have in this paper, it looks roughly something like this first case, right? Which means the denominator is, well, smaller by 1. More specifically, the denominator is a linear term. So if we have a linear denominator, here's the nice thing about it. We can actually skip using long division, and we can use synthetic. So it's safer to always use long division, but if it's a special case, and the 2 cases we have are not every case, we could have something where it's going to be squared on the bottom, and synthetic division is no good, but we can use synthetic on the 2 examples we have because our denominator is going to be x and x plus 1. So ultimately, when you use long division with this special case, we're going to get some quotient out of it. And the quotient's the only thing we're looking for. Remainder is not going to play an effect, just the quotient. So once we have that final quotient, we don't need to do that last step to find out what the remainder is. It's not going to actually affect the asymptote itself. So let's work through one of these and see what we get. Number 10, again, first things first. Vertical asymptotes are going to exist. It happens for us to be at x equals 0. So x equals 0, at y-axis we have that asymptote. Now the degree up top is larger than down below, so that should already be a trigger. It's not horizontal, and it's greater by exactly 1, degree 1, degree 2. So we're going to use, and in this case I'll use long division just so we can kind of see what it looks like. So ultimately, let me make note, for our slant asymptotes, we're going to, fix that, that's horrible handwriting with that. Slant asymptote, we're going to do some long division. So x into 3x squared, and plus 0x, right? We need that placeholder plus 1. Well, x times what is 3x squared? 3x. Multiply it, we get 3x squared is a 0. We bring down the 0x, so 0 times what is 0x? Well, plus 0. That doesn't really help us with anything. So what we get as the quotient, again, the remainder does not come into effect when we're looking at slant asymptotes, is this guy right here. So that y equals 3x. So what do we do with this? Well, we graph it. It's called a slant for a reason. It's not horizontal, it's going to be at a slant. So we're going to graph the line y equals 3x. So 0, 0, right? Plus 0, it's our y-intercept. And a slope of 3. 1, 2, 3 over 1. So now our two asymptotes are this slanted line of y equals 3x and our vertical asymptote of just the y-intercept. So we get these two. Now from this point, it's no different than our rest of our rational. We want to test a few points. So I'll test -1, -2. But I don't know where it's going to be graphing. It's going to be this really wide piece or this little sliver. And I'll do the same for 1 and 2. F of 1, F of 2. Can definitely do it by hand. But again, graphing calc is going to save you a lot of trouble. F of -1 is -4. So -1 we go down 1, 2, 3, 4. F of -2 is -6.5, so -5, -6, -7. And then f of 1, 6.5. F of 1 is going to give me 4, and f of 2 is, it's not 6.2, it's 6.5. So f of 1, we go up 4, 1, 2, 3, 4. And f of 2, positive 6.5. Now this one's kind of unique and kind of cool, right? It's symmetric in a bunch of ways. You're going over from the origin equidistant on both sides, and you're either going up or down those same amounts, which we should expect because we have no change from that vertical asymptote. So if we have a couple points sketched in there, if you need more for the general shape, then absolutely, especially with a graphing calc, test a few more points. But instead of it being perfect quadrants, it's still kind of quadrants though, right? We have 1, this little sliver of 2, wide piece of 3, and then 4. I know both of mine are going to land within these skinnier pieces. And again, never going to cross any of the asymptotes that they are working on. Now if we were to talk domain, domain would be the same thing as before. All of our domain issues come from vertical asymptotes, not from horizontal or slant. So nothing changes there. It'd be from -infinity to 0, and then from 0 to infinity. So I'm going to have you guys try number 11. Again, I did use long division here, because it's always better to be safe than sorry. But if you do recognize it's a linear term as a divisor, then you can feel free to use synthetic in order to get that quotient. And again, remainder does not come into play for slant asymptotes. So give it a try, number 11. I'm letting you know it will be a slant asymptote. And we can already see that, right, because our degree up top is 2, which is exactly 1 more than our bottom denominator degree of just 1. So give it a pause, give number 11 a try. So once again, we come back, and I have our second case, our second example worked out for us. We're just going to kind of walk through it. Looking at number 11, I can start no matter what. Before even looking at vertical, horizontal, I can always find, horizontal slant, I can always find my vertical asymptote right away. So I can always look at the denominator. Top isn't factorable, so we can't get anything else to cancel out. So it's just that x equals -1 for that vertical. Now looking for slant or horizontal, again, we already talked about top degree is larger by 1, so it's squared over linear. So we're going to need to use division. Now if it's over something linear like this, then we can actually skip long division and use synthetic. So that's what I do. I have my -1, 3, and 2. And then the 0 that I'm using in there, let me darken this up a little bit, That's what's coming from the bottom. That's that x plus 1 equals 0 or x equals -1. So we do synthetic, bring the -1 down, multiply by +1, bring that down, we get 4. We can stop right here. Reminder, the remainder is no help for us. So we don't even bother finding that when it comes to slant asymptotes. So now I translate that back to something that's an equation, -x plus 4, and then this is our slant asymptote. So y-intercept up at 4, slope of -1, and then we get this new kind of diagonal dashed asymptote. So from there, we tested points. I did -3 and -2, but they both give me the same value of 8, which I thought was kind of funky. And then I did the points 0 and 1, and they both gave me the value of 2. I thought that was also kind of funky. So I did a point in between both of those. I did f of -2.5, and I saw it dip down just slightly, so that's our bottom dot right there. And then I did f of 0.5, something in between these two, and I saw it just went a little higher than 2 at 2.2, so I know I'm getting that curve. It's not just necessarily flat. So again, this is a case of, even though I'm almost sure I know the shape of that graph, I'm just testing at least even one more point. It kind of gives us that little extra bit of detail. Then from there, I got the 3 points in their respective little quadrants, and I know the general shape is not going to cross the asymptotes on the top and the bottom. And then just like number 10, not going to work it out for domain, but if we needed to, it's only being affected by our vertical asymptotes or any holes we have. So it'd be from -infinity to -1, and from -1 to infinity. So now we're going to take all this stuff we know about rational, and we're going to give it a little application. For the application on the last page, I have slightly different question I put on the board. Same question, I just worded it slightly different, just to kind of give some more terminology. For one, we have a page that contains 57 square inches of print. So on that little drawing, that's that middle piece in here. So the area of the inside has to be 57 inches squared. We know all of the margins are 1 inch deep. So from here to here is 1 inches, here to here is 1 inches. So all the way around, all of these are 1 inch. And it's asking us to find the dimensions of this page, where it's going to have to maintain those 1 inch margins, to have the least amount of paper used, and where you might see it in this class, you'll see it, and definitely in calculus, it's asking us to kind of minimize the amount of paper used. And we like this word minimize because we've done maxima and minima before, so if I kind of relate it now to this, it'll help us out a little bit. But first, we gotta produce something, right? How do we do this? Well, with any application, you start with what you know. So the first thing we do know is we do know the area of the inside page. Now, if I were to call the horizontal measurement my x and the vertical measurement my y, then I can kind of help find my area. So I'm going to start there. I know my area of any rectangular page is just x times y, right? But I'm also given what that area is, which is 57 inches squared. So I know that for now, and I'll kind of leave it be. I don't think there's much I could do. I could get x by itself and divide y, or I can get y by itself and divide x. So we'll see what else I can do. Well, I started with area of just the page itself. It tells us what the margins are, so let's try to get the area of the entire thing with margins included. Well, it's not just going to be x times y, right? Because our x now has a margin of 1 inch to the right and the left. So our original x measurement is now going to be increased by not 1, but 2 inches, right? 1 to the right, 1 to the left. And then similarly for the y, it's not just y is going to be increased by 2 as well, 1 inch up top and down below. So if we have our original area inside the page, the area of the entire thing is just including those margins for us. Well, we ultimately want this, right? we want to be looking at this because if we're trying to find the least amount of paper used, it's the least amount of area, least amount of material. So we really want to deal with whatever this function is going to be. Now, it's not much use to us so far because we don't know A, we don't know the X or the Y, but we did already produce a little bit in the beginning. So I know I can get Y in terms of X or X in terms of Y. We'll just get the Y in terms of X. And we'll see why we're doing that in a second. If I just divide the X over, I get Y is 57 over X, and that's what we know. Now here's the nice thing about that. If I substitute that in for this Y, then that means the only thing I have to worry about is that variable X. So it's only one variable that that area is in respect to. Now becomes something more that we can work with. So I'm going to make that substitution. So X plus 2. Now Y is 57 over X. Let's make this a little bigger. 57 over X plus 2. We need a common denominator. We have X plus 2 now times 57 over X plus 2X over, oops, not 2 but X. I'm going to clean it up a little bit more. We have X plus 2, 57 plus 2X. And really, all of this is over X, right? Because this term will just multiply by the numerator. Now I can keep going, but this should start to spark a little bit of something we've seen before, maybe we just spent the last little bit of time lecturing about. We just created a rational function, right? In fact, if we were to multiply this out and continue doing it, we would have X times X squared, so, or say X times 2X, so 2X squared. We'd have a middle X term. We'd have the 2 times 57, so 114. We'd get something quadratic up top. And then we would get something linear down below. So we get something roughly that's quadratic up top and linear down below. Where did we see that before? What we just did with slant asymptotes, right? So we produce something that is going to be rational with slant asymptotes. Now, before we kind of find this value, I'm going to take 1 second to talk about the difference of these two cases. If we have more traditional rational graphs like this, right, we don't really have any local minimum. It's either dropping off forever or slowly kind of reaching out towards infinity. So if the degrees were the same or greater down below, we get something like this, but we have no way to find the least amount or minimize that. However, because ultimately this will be something in the form of a slant asymptote, let's just say it looks like this. Make it a little more dramatic. Say it looks like this, and then something like this. The nice thing about it is we either get this maximum here or this minimum here, because with those slant asymptotes, we have to have something that's a little more steeply curved. And thankfully, we get something of this form. And the graph is exactly what we want to be looking at. So at this point, we could do it by hand, but we do have the graphing calc for a reason. We might as well use it. We can go on ahead and type this function into our y equals. And then we can go and try to graph it, but we're going to see we're not really seeing much. So in order to make that change, if we hit zoom in the top middle, we can scroll down and we can have at the very bottom zoom fit, which is really nice, or just go to window and change the window until we kind of see that whole function. Now, we'll see as I just kind of drew, it is something with a slant asymptote. And we already did this in chapter 1, and also in chapter 2, at the beginning of it. If we're trying to find a minimum, well, that's already a tool in our graphing calc. If we go to second trace, which is calc, we go down to number 3, that was that minimum, where it just wants us to guess something to the left and something to the right. So where we had this graph kind of looking like this on the graphing calculator, for me, it looks something roughly like this. I really want to know what is this minimum right here. So we're being asked to find the least amount or minimize it. So in doing so, you do that second calc, minimize. I'm going to do a left bound. I'm going to guess 0. just because it's anything to the left. To the right, I'm going to guess 10, and then I'll guess 5 in the middle. And when I do that, so when I minimize this guy, I'm getting that x is roughly 7.5. So if I get x is 7.5, then if I'm going and need to find y, I can plug it into this. Well, if I do 57 divided by 7.5, I'm going to get roughly y equals 7.6. So now I have the two dimensions that minimize the dimensions of the page. And then if I wanted the minimal dimensions of everything, including the margins, well, what do? I would just add 2 to the x, so 9.5, and then 2 to the y with 9.6. Now the big thing here is that we produce something rational, which we're using, but more importantly is that it was something with that slant asymptote so that we could do this idea of minimum or maximum. Now, applications I know are the tough ones in any section, so what I suggest is always use what you know. If it's telling you something about area, then we should be producing some type of function about area, say if it was perimeter or anything else. But that wraps up our lesson on 2.6.